You ever have that feeling, that product that worked perfectly on your bench, passed every single quality check, and then it just fails catastrophically out in the real world? It's a massive problem in industries like aerospace, defense, and automotive. Basically, anywhere that reliability is everything. So let's dive into that invisible but absolutely critical gap between the software simulation and the hardware reality. Because that's exactly where perfect products go to die. And this gets right to the heart of it. That green check mark from QC, yeah, it feels great, but it tells you absolutely nothing about how your device is going to behave when it's freezing cold at high altitude or baking in a desert. The defects that actually kill electronics in the field, they're often completely invisible at room temperature. This leads us to the first major problem, something I call the deceptive pass. It's that really dangerous false sense of security you get from a successful test in the cozy, controlled environment of the lab. This slide just lays it out perfectly. On the left, you've got your simulated code. It's beautiful, right? Clean, the logic is flawless, timing's perfect, it gets that big green check. But then look at the right. That's what happens when the exact same code meets real-world hardware. All of a sudden, you've got jitter, you've got noise, unpredictable signal defects. It's a complete mess. That space between the two, that is the critical defect zone. So let's put a name on this thing. We're talking about the hardware/software gap. It's this massive chasm between your pristine firmware that runs like a dream in a digital sandbox and how it actually behaves when it has to control physical parts that are being pushed to their absolute limits by temperature, vibration, and all sorts of electrical noise. So where exactly are these failures hiding? Well, to find out, we need to go exploring in what's called the hidden failure zone. Take a close look at this diagram. The real danger isn't just buried in the physical hardware layers, the copper, the substrate. And it's not just in the code itself. The most dangerous failure zone is the interface. It's that spot where the firmware's logic actually has to execute on a physical chip, sending real signals through a real board. And this is just so crucial. When the temperature plummets, the actual physics of the silicon changes. Electrons literally move differently. The precise voltage that the chip reads as a 1 or a 0 starts to drift. That can corrupt your data. And at the same time, the timing of critical interrupts can shift just enough to make the software miss something important or run things out of order. Your standard bench test at a comfy 25 degrees Celsius, it's completely blind to all of this. So, all of this brings us to the consequences. Let's take a look at what happens when good code, under real pressure, just goes bad. This graph. This tells a terrifying story for any engineer. Over on the left, at normal temperatures, the system clock error is tiny. Everything's stable, everything's happy, but watch what happens as the temperature starts to climb. The error begins to drift wildly, entering this chaotic timing drift zone. This is the exact moment where systems just completely fall apart. And that chaos you saw in the graph? It isn't just a squiggly line. It translates directly into these kinds of catastrophic failures. Your real-time operating system starts missing its deadlines. Tiny memory leaks that you'd never see in a short test suddenly cascade over a long mission and crash the system. The device hits some weird edge case it's never seen before and throws an unhandled exception. Or something as simple as vibration creates enough signal noise to crash the entire firmware. Okay, so we have really defined the problem. And yeah, it's a scary one. But there is a way to find and fix these hidden flaws. So it's time to talk about the real-world stress test. I absolutely love this quote because it completely reframes the goal here. We're not just trying to get a pass or fail grade. Environmental stress screening, or ESS, is really a process of purification. It's designed to actively find and force out those latent defects so you can eliminate them before a product ever leaves the factory. Think of it as a filter for unreliability. But here's the critical insight. This is the part most people miss. You can shake and bake your hardware all you want, but if you aren't watching what the firmware is doing at the exact same time, you're still blind. You're only testing half the system. The real magic happens when you monitor the software's behavior while it's under stress. And that, right there, brings us to the solution, what we can really call the ultimate reliability fix. This is it. This is the aha moment. It's not just about running your code and seeing if the hardware survives the stress. It's about actively monitoring the firmware's output, the signal integrity, the timing, the data packets, while the device is being hit with extreme temperatures and vibration. This lets you see the exact moment a timing conflict or jitter shows up. So how does this actually work? Well, it's a pretty clear four-step process. First, you integrate the final firmware onto the actual target hardware. Simple enough. Second, you apply the stress, the heat, the cold, the shaking. Third, and this part is key, you use precise tools to measure signals and decode data protocols in real time. And finally, you analyze all that data, correlating jitter and timing errors directly to what the firmware was doing at that exact moment. This is how you find the failures that everybody else misses. You can literally see the precise temperature where a software output gets corrupted. You can pinpoint the exact G-force that causes the firmware to crash. You catch those tiny little RTOS timing glitches that only happen at -40 degrees. You finally get the full picture. So why does all this matter? I mean, think about the business impact. You basically eliminate those early infant mortality failures. You dramatically improve the mean time between failures, which is a core reliability metric. And that means less warranty exposure, higher system availability, and most importantly, it protects those mission-critical deployments where failure is just not an option. So I'll leave you with this one critical question to take back to your team. I want you to take a hard look at your validation process and really ask yourselves, are you truly testing your entire system, the hardware and the software working together under stress, or are you just testing your hardware? Ultimately, closing that hardware/software gap isn't just good engineering. It's the only way to build products you can actually trust. If you want to take a deeper dive on how to implement this kind of functional monitoring, the team at BMO Analytic are the real experts. Because at the end of the day, it's all about making things reliable.